Hi guys, welcome to another Mr. Fourth Dimension video. This is an episode of the Geo project. Last time we did some work with the math functions and we were working on the direction function, and I have to go back and do one more correction on the direction function because I found out after I thought about it, I remembered and I did a little research that I totally am doing it the wrong way. So we're going to change how we're doing direction one more time. And what I screwed up is that there's an ATAN that takes two arguments. And that version of ATAN, well, if you remember, the one argument version of ATAN just takes in an argument that's the slope, and it gives you an answer for an angle in one of these two quadrants, right? The x is positive quadrant, or half of the math graph thing. It gives you an answer in one of those two quadrants, but it doesn't even give you, like, for vertical lines. It can't handle because you can't represent that as a slope. The ATAN 2 works completely, and what it does is it takes in a y and then an x, so that it's not like it's not one argument, but it takes in the y parameter and the x parameter separately, so it can figure out if you need a vertical line and if you need like a negative x direction over here, right? It gives you the right answer in the full roundabout the circle. The other thing it does do that I don't think makes any sense is it ranges from negative pi, like in this way, right, from negative pi to pi. And that's weird because the way you normally think about degrees, or like about angles when you're doing degrees, is like this, right? You put the parenthesis on this 360, and for some reason they put the parenthesis here. It just makes it a bit weird. Not a big deal, because all we have to do to make this work is add pi to it whenever they have one of these that's negative, right? So that'll, whenever it's negative, we'll just add pi, and we'll get the answer we want, which is going to be 0 to 2 pi, like so. Okay, so let's go make that change. We're also going to need to make the change in the math functions, but we're going to just separate these out, and we're going to assume that we're going to use ATAN 2 with those. Now the other thing I was thinking we could do, actually, while we're here talking about it, is not even do any work in this. So this is almost just an inline at this point. And the reason for that is that we are making the separation layer out in the GeoMath so that it can be for optimization purposes, right? So the idea is that the user of the library can fill this function in however they want to make it faster for their platform, to remove dependencies from C library if they want, or whatever reasons they have, they want to do the work here. Well, if I use the ATAN, which is defined as, negative pi to pi, like this, and then I convert it here, then that means in my definition of math ATAN function, math ATAN is defined to have this range. Right, so then I'm going to take that math ATAN function that has that range, and I might do an if on it. Right, I'm going to do like an if p dot y is less than 0, then we're going to add pi like so, right? Otherwise, don't add pi. Or that should be add 2 pi. Yeah. And if I do this here, what's going to happen is someone might come along and go, hey, here's math ATAN. I'm going to make my own optimal version. It's not the C standard version, but my own optimal version of ATAN 2, right? And it goes and this implementer looks and sees that this math ATAN has to output between negative pi and pi. Okay, so what if the optimized version they had would have most naturally ranged like this? Right? If that was the natural range, they're going to have to do the subtraction. They're going to do an if and a subtract, and then we're just going to do an if and an add anyway. So since we're expecting this this function geodirection to range from 0 to 2 pi, I'm saying let's make math ATAN range that way. So we'll do a little bit more work on the math side of the divide. That way, if someone comes along with an optimal way to do that without doing where they don't have to do a subtract to find it, but it's just directly finds the correct answer in that range, then we can skip out this whole if stuff, and we have a nice fast geodirection function for them. And for those of us who aren't using an optimized math ATAN, it's still just as fast as it would have been no matter which side of the divide we put it on, if that makes sense. Hopefully it does. So this is going to work something like, whoops, what's that all about? Got my insert key accidentally. Math ATAN 2, p dot y, yeah, well, this should be y, this should be x, and then that should be y. So if y is negative, it adds 2 pi so that it's in the positive, over pi, like larger than pi range. So it'll range from 0 here all the way around, getting close to 2 pi and then there. So let's test this again using the test code we have set up. We'll start with a positive y. Hopefully it builds. What do we got? Right, of course. Let's move the pi into the math header. That just makes sense anyway. And this isn't technically a header. I did make a statement last time that I ended up changing off screen, which I changed this into a CPP. It wouldn't have compiled if I tried to compile it. Alright. So with y being positive, it's ranging from there to there, and it's the same numbers we had last time, so I'm trusting that that works. Let's do another test. We need to test y being negative. And again, it's the same numbers as last time. That's a little bit below pi. That's a little bit, or it's a little bit above pi. It's a little bit below 2 pi, so it's the right range. This is the one that always gets us. Let's see if it's working correctly this time. 0, 0 is coming out as a 0. Well, that's just how the ATAN2 function decided to define it then. Because again, 0, 0, the direction to that is, you know, not really a well-defined concept. So you're kind of free to do it however you want. We've been doing it where it's like halfway between this on the spectrum, but just not having that halfway between mark and just making it 0 also makes sense. Actually, that might make more sense. I don't know. If it's faster, then it doesn't really matter, because we're going to try not to ever rely on something that uses that anyway, because it's mathematically undefined. So, that finishes our geodirection function the right way for the last time. We don't have to come back to it. So, the next thing to do is to talk about angle functions. And so the difference between a direction and an angle is that a direction is sort of like an absolute direction in absolute space. So 0 means this way, right? And pi means this way, and pi over 2 means up, right? That's a direction. An angle is more like we have a pair of points that we're imagining make an angle with the origin, or more likely we have 3 points that make a sort of angular shape, and you want to ask different questions about the inside angle or the outside angle that they form. Now in geometry this kind of work is easy because we can just look at the shape and go, hey, like this is the inner angle, so measure that. With a computer, it's not quite as obvious all the time, especially when we start dealing with polygons and stuff. But even just as things are, if I take an angle and I ask what's the size of this angle, it might report to me the large one if we're not careful about how we go about computing that. So let's do a 3-point angle function called positive angle, and I'll explain why we're calling it that and what it does as we work on it. So it's 3-point. That means we're going to call it 3-point angle, and it'll have like a point 1, and then it'll have a center, and then it'll have a point 2, something like this. Maybe I'll call it ABC, because that's what you often do in geometry when you have like angles, or yeah, when you have an angle, they do like the notation. It's like the angle from formed by ABC. I don't know. It's been a while. I'm not sure if that's the notation that I'm thinking of or not. Yeah, they have like the angle symbol, and then it says ABC after to the right of it. But the idea is for this is the 3-point angle positive. So that means it's going to take the angle that you form by going from B to A, it's going to take that direction, and it's going to figure out, rotating around positively, how far it has to rotate to get to this angle. So, say I have the simple case. Say my A is like right here, and my C angle my C is up here, right? So A, C. So the positive amount is like some amount that's like less than a quarter turn, right? But now if I flip them, I make this the A, and I make this the C. Now A is going to go past pi. It's going to go halfway around the circle and then keep going to find its way there. So with the order we put them in, ABC versus CBA will matter in terms of whether we get the small angle or the big angle for this function. This function's job is just to find the positively oriented angle. So to do that, basically what we're going to do is we're going to take the angle to A from B to A. So to take the angle from B to A, we want to do a subtraction. We'll call this direction A, or yeah, we'll call this adjusted A. So I don't want to. I'm trying to think of a way to denote a second version of A. A2, A prime. We'll just call it AB maybe. And this is going to be basically A minus B. Now we don't have overloaded operators, so what I actually have to do here is A dot x minus B dot x, A dot y minus B dot y, right? And then we'll do the same thing for C. We want a CB. That should be B still. There we go. So I'm thinking one thing we might want to do is define addition and subtraction operators for these points, because that'll make our life easier in a lot of, because we also do something similar up here. I think we've got, like, we could do a subtraction and a times and a plus, and if we can optimize it so that it comes out, I don't know, like, maybe it can't be quite this fast if we do an operator overloading for this one, so we want to, like, think about it. And same again here, can we make this, actually one thing we should do is try to use multiplication instead of division. If we're going to talk about operator overloading, that'll make our life easier. 0.5f, why is that so hard? Okay, got it. Anyway, focusing on this 3-point angle, so we have the ability now to take the angles, or the directions to both of these. So this will be the direction to A equals geo direction to AB, and the direction to C equals geo direction to C from B, right? So now we have some directions. Let's label these with dir A, dir big C. Okay, so just be a little more explicit. Now, the next trick is imagining in the simple case that dir C is in the positive direction from A, right? It's not like A is not here and C here, so that A has to go past the 0 point and keep going. But if C is, well, basically the simple case is we just return dir C minus dir A. This will work whenever A, or that should, yeah, that'll work whenever A is less than C, like we're expecting. But if A happened to be larger than C, then what we want to do is a little bit different. We want to add 2 pi to that result. It's not we want to flip it, right? Because we're not trying to take the smallest angle or something like that, or the that wouldn't even be the smallest angle. It might be. I'm not sure. We'd have to think about it to be sure. No, it would just be the angle that avoids crossing over 0. It wouldn't actually be that meaningful. No, what we are doing here is we have direction A. Say direction A goes this way, and direction C. So if direction C is larger than direction A, then that means that going positively, we will eventually find it, and we'll never have to cross over the 0 2 pi threshold. But if it's flipped, if this is A and this is C, then A will be larger than C, and we will have to cross over that threshold. Meaning, if we do the subtraction here, we'll get a negative amount. Right? We'll get dir C minus dir A would take us to the negative amount, basically, between the two of them right there. So if there's, like, say there was 90 degrees between C here and A here, we would get negative 90. Then if we take that and we add 360, I'm switching to degrees because it's easier to think that in that way, and then we'll just use the addition subtraction rules we come up with. Right? If we add 360, boom, you find out that you're actually going 270 in the positive direction, which is the answer we want. So basically the rule is, if dir C is greater than or equal to dir A, we use this rule. Else, we're going to use dir C minus dir A plus 2 pi. Right, so that's how you do a positively oriented angle measurement. Let's also do a negatively oriented angle measurement, and we'll have to test it next time. A negatively oriented angle measurement sets up exactly the same way, and then the only difference is in a negatively oriented angle measurement, if I have A and C, right, I actually want a positive answer still, but it's the positive answer for how far you have to move in the negative direction to get from A to C. So if A is larger than C, that's the easy case, and then you just do the dir A minus dir C. Otherwise, we do dir A minus dir C, probably plus 2 pi, because we're still looking for a positive. So if A happens to be less than C, so here's A, here's C, and there's 90 degrees between them this way, and I want the negatively oriented angle between them, that means I'm going to move this way, and I should get an answer of 270. But if I do dir A minus dir C, right, what I'm actually going to get is a negative 90, but once I add 360, I get back to the answer 270. So that should be how we do the negatively oriented angle. So I think we've got some good stuff. We'll need to start by testing it next time, but hope it's been interesting. See you guys next time.